Welcome back. Today we're going to talk about the implementation of digital filters. And we'll start with the difference equation. The way it's written here is slightly different than other ways we've sometimes seen it. In fact, there are two ways of writing this in general. One is to put all the y's on one side of the equation and all the x's on the other side of the equation. The other way, and the way that the book uses a little bit more, so I'm switching to this method, is to put yn is equal to the sum of the a's times our y terms. Now, this doesn't really matter. It's just an algebraic manipulation. What matters is the sign of the a's. Some versions, sometimes you might see this equation with the sum of the y terms on the left side and the a's positive. If that's the case, then moving them over to the right side would make them now negative. But that negative sign could be absorbed into the y's, or into the a's, and it could be written this way with the a's still positive. And that's what the book is doing, so that's what I'm going to do right now. Once again, if you're ever implementing this, say in MATLAB or C or Python or whatever language you've got, and there's a function for filtering, you need to know which convention they're assuming. Are they assuming this method, or are they assuming the method where the a's would be on the left side, and therefore when you actually calculate y, you would negate them? So check the documentation to make sure you're consistent. Well, based on this, we can write our system function as h of z is equal to the z transform of the x terms over on the top and the y expression on the left. So this negative sign here comes from the fact that when we find the system response, we have to move the y terms over to the left hand side, and so now, whereas they were positive, now they become negative. Okay, this we're actually going to look at ways of implementing filters, and they all come from different manipulations, or many of them come from different manipulations of this equation. So manipulating the z transform system function will give us suggest specific implementations. One of them, for example, would be to simply factor this into our poles and zeros. And here we would get 1 minus ck, z to the negative 1, and 1 minus our. So the poles and the zeros, these terms may be complex. In fact, usually they are complex. So not just maybe. We could also factor this, or do this differently. This is a little bit easier. This way. And ak z to the minus 1 times k equals 0 to m bk z raised to the negative 1 power. In this case, we'll call this first term hp of z, and this one hz of z, for the poles and the zeros respectively. Note that since y of z, the transform of our output, is going to be h of z times x of z, with this second factorization we have that is hp of z times hz of z times x of z, which suggests that we could do that first and get an intermediate term we'll just label v. And so we're essentially applying two filters. The first filter is going to be the feed forward filter, and the second one will be the feedback filter. So let's follow up on that just a bit. This would give us a Vn associated with our V of Z is just equal to the filtered version of our input with our feed forward filtered with our feed forward filter with our BK terms, and then the output Y is just the filtered version of V, which would be V of N plus this sum from K equals 1 to N AK Y N minus K. And graphically then, we have HZ of Z followed by HP of Z. The intermediate term is our V, and the output term is the Y. Now that we have it factored this way, admittedly this wasn't some brilliant insight. It's a pretty straightforward way of thinking about the problem, but it's a good start. Now that we have it factored this way, we can draw a block diagram representing these same actions. Okay, so here we have the first part representing H of Z. So just to walk you through here, we have the input X of N, and with no delay, so just straight up X of N is multiplied by B0. That's added to the other terms, which we'll discuss next. We now delay X of N by 1, following this downward path through Z to the negative 1. The delayed version is multiplied by B1 and added up. It's delayed again, so now the total delay is 2, and it is multiplied by B2 and summed up, and we continue that on for as many B terms as we have. When we're done, the summed up version is V of N. And now we're going to go into the feedback version. So the feedback sums V of N with all the feedback terms. So the feedback terms, we take our output Y. I paused the video while I drew the last one, but I'm going to make you endure this one to motivate what we're going to do next. It's kind of tedious. Leave -1. If you typically speed up your video, now is the right time. This is going to come over here, multiplied by A1. Multiplied by A2. And now we will sum up these things on the way back through. And there we are. So now we take the output, we delay it by 1, multiply it by A1, and add it back to the input. Delay that same output again. So now we have a delay of 2, multiply that by A2, and sum it up, and so on and so forth. So this is the block diagram of this system. This would be yn-1, yn-2, x-1, x-2, and so on. Well, this is the block diagram, and because it's tedious to draw one of these, there's another method. Once again, no fancy insight, but this other method is to actually, it's called a signal flow graph, and it does essentially the same thing, but instead we just say x of n comes in here, 5 on the way out. Anytime we have a multiplication, we just put an arrow in the middle of the line. z to the negative 1. We'll put one here too. Z to the minus 1. And here we multiply by our coefficients, b2, b1, and then we've got a b0 up there. Sums are just denoted by nodes. Usually it's obvious which direction the signal is flowing because of the arrows we use for multipliers. But if it wasn't obvious, you could put arrows as needed to make it more so. So sums are just these nodes. You can put a node also in a place like this where it's not summing but it's splitting. So the node there shows connection. Z to the negative 1, Z to the negative 1, A1, A2, there's Vn. And so this is the same system using a signal flow graph. Took much less time to draw. Now this particular implementation is given a name, and it's called Direct Form 1. And we'll see that Direct Form 1 is fine, but there are other implementations that we can use by manipulating things a little bit differently. And so that'll be the subject of our next lecture.